have to find the moment of inertia of a distributed mass body about this axis, about any axis. So what we do is, first we break it into very small particles whose mass is almost equal to 0 but not equal to 0. They are so small that is the distance from this axis is same. That is of this particle so small, you cannot say that it is so big. Then the distance from this axis that is going to alter, is going to be different. But this particle is so small, this is a particle, this is so small that is dimension, this is a point mass body. So it is going to have this dm is having a fixed distance from this, that is r. Moment of inertia of this from this axis is dm into r square. Once again we have used the same formula. If you have to find the moment of inertia of the whole body about this axis, then we integrate it using the right limits and we can get the answer. Let's understand it by taking an example of a thin uniform rod of mass m and length l when the axis is passing through its one of the ends and perpendicular to its length. So that is how we define moment of inertia about which axis. That is very important. If we simply say moment of inertia of this rod, it can be axis can be anywhere. Axis could be here also, axis could be here also, axis could be here also. The moment of inertia, though it depends on mass, but it is more important that is how the mass is distributed about the axis. Moment of inertia of this rod about this axis is different when the axis changes from here to here. Even when this rod it makes some angle, then moment of inertia of this rod about this axis, that is how the mass is distributed over the axis, that is changing, so moment of inertia will change. So moment of inertia primarily depends upon that is what is the mass and how it is distributed about the axis. Let's find moment of inertia of a rod about an axis passing through its one of the ends and perpendicular to its length. So this is the rod, this is the axis. Remember that this is a thin rod. This is applicable only for thin rod. We have, this is thin rod and we are finding the moment of inertia about y dash axis, and this is thin rod, its total mass is m and length is l, and this is uniform mass distribution. We are finding its moment of inertia about its one end. Let's take, so first thing is we can use that is mass per unit length. Mass per unit length. Why we have taken mass per unit length? Because eventually we shall be taking a small particle of mass dm and we shall be finding the moment of inertia of this generalized particle dm r square about this axis, and then we will take the limits and integrate from here to here. From lower limit, that is from here to here, we integrate it and then we find the moment of inertia of this whole rod. Now if the total mass is m and total length is l, so mass per unit length is m by l. Suppose this is a 20 kg rod, mass is 20 kg and length is suppose 10 meter. So it means every 1 meter has a mass of 2 kg, that is 20 by 10. Mass per unit length is going to be 2 kg per meter. If someone has taken and cut a portion of 3 meter, so the mass is going to be 2 kg into 3 meter, and 3 meter, meter cancel, it comes out to be 2 into 3, 6 kg, right? So this way we can find what is the mass of a particular length. Over here we say that is total mass is m, total length is l, uniformly mass distribution, so it is m by l, that is mass per unit length. So now what we generally, that is how integration is done, is at a distance x we have taken this length as dx. This is a very, very small length dx and this has a corresponding mass dm. It is going to be in kgs. The dx is length, x is also length only. So mass per unit length, if you say that is dm, what is dm? Mass of this dx is total mass upon total length into dx. That is what we have done. If someone had said that is mass per unit length, whenever say that is mass per unit length is 2 kg per meter, and if someone says what is the mass of 3 meter, so what we do is 2 kg per meter into 3 meter, this mass per unit length into length, meter get cancelled and this comes out to be 6 kg. Similarly over here the mass per unit length is m by l into dx into that is length of this. M by L, over here it was 3 meter, over here it is dx meter. So m by L into dx, what does it make? Dx is so small, so it makes dm also, that is mass also of this differential element of mass. So this is dm, mass of this small section, small particle, it comes out to be m by L dx. Now we know that is moment of inertia of this particle about this axis is going to dm into r square. So moment of inertia of this about this axis is going to be that is dm, that is m by L dx into x square. of this general particle, the distance is x. Now we integrate it. Very first particle is over here, that is at x is equal to 0. We integrate x is equal to 0. Then moment of inertia of this particle about this, about this particle about this, about this particle about this, plus means integration only. We have to add it, integration only. We have added from here to here to here to, and last particle is over here at x is equal to L. So over here x is equal to L. So this is moment of inertia about the y dash axis. M and L, they are constants. So this comes out to m by L. So this comes out to be x squared dx. So this comes out to be m by L. Obviously x is equal to 0 to x is equal to L. So this comes out to be x cubed by 3, 0 to L. So this comes out to be ml square by 3, that is moment of inertia about the y dash axis. First you put upper limit. So this comes out to be m by L, L cube by 3 minus, then you put the lower limit, that is 0 cube by 3. So this comes out to be ml cube over 3l, and that comes ml square by 3. It is very basic integration what we have used. So moment of inertia of this thin rod about an axis passing through one of its ends and perpendicular to its length is ml square by 3. Now you can find moment of inertia of this rod about any axis. We can also find the moment of inertia of this rod about an axis which is passing through its center of mass, about center, and perpendicular to its length. If we have to find the moment of inertia of this rod, so L by 2 is here, about center, so L by 2 is here. This angle is 90 degree. This axis is y dash, so y dash at a distance x. Once again, we take a small distance dx. What is the mass per unit length? Total mass upon total length. So it is m by L. Generally, many times students what they do is, that is, if we are considering this, they take mass as m by 2 and length as total L. No, if mass is taken over here, that is to find the mass distribution per unit length. If you are taking this as m by 2, then length is, corresponding length is also L by 2. If you are taking the whole mass, then this mass by length, obviously that will remain same. That is not going to change. Mass per unit length means that is the mass for every unit of length, this is going to be remain same. Whether you take a small section or you take the whole section, it is going to remain same. So mass per unit length is m by L. Its mass is dm. So dm is once again m by L into dx. Moment of inertia of this particle of mass dm about this axis is dm into x square, that is m by L dx into x square. Moment of inertia from here to here is 0, x is equal to 0 to L by 2. It is right in the middle. So whatsoever the moment of inertia of this section is the same of this section. So we find the moment of inertia of this portion and then multiply by 2. This comes out to be 2, m by L we can take it out. So this is x cube by 3, it comes out to 0 to L by 2. So this is going to 2m by L, 3 we can take it out, 3 we can take it out. So this is L by 2 cube, that is L cube by 8 minus 0. So this comes out to be ml square by 12. If you wish to take the integration limits from here to here, you don't wish to double it, that is what's the moment of inertia about this axis of this section, because the same section L by 2 is here, L by 2 is here, then you could have also done it. Let's say the rest remains same, that is m by L dx into x square. Then the limits could have been taken from x minus L by 2 to plus L by 2, and this will also give as ml square by 12. The moment of inertia will not change. If the axis, if the distance is L by 4 here and 3L by 4 here, so what you can do is now to find the moment of inertia about the y dash axis. That is, if you find now about y dash axis, rest will remain same. You will take the limits as x is equal to minus L by 4 to x is equal to plus 3L by 4. You can integrate it and you can get the answer. So this way you can find the moment of inertia of rod about any axis you are interested in. If you have to find the moment of inertia about this axis, that is y dash, this is L, mass is m, and from here to here, suppose it is small l. So what we do is, once again, we take a small section of length dx at a distance x from this axis. So dm, that is differential element of mass, is m by L into dx. That is the mass of differential element of mass of this differential element of length. Moment of inertia of this particle about this axis is m by L dx, that is dm. We know it is dm into r square. This is dm into r square. R square is what? X square. What are the limits? Limits is now it is not 0. The first particle is over here, that is x is equal to L. It is situated at distance L. And the final is at x is equal to, that is L plus capital L. You can integrate and you can get the answer. Now over here, suppose this rod, thin rod of mass m and length L is inclined like this. So what we can do is, once again, at a distance x, we can take a small section of length dx. It has a mass, differential element of mass as what? Once again as m by L dx. This is the differential element of mass of this particle. So now what is the moment of inertia of this particle about this axis? So y dash, let's say if we talk only of this particle, it is going to be, we know, it is going to be dm into r square, where r is the perpendicular distance of this particle from this axis. So it is not this distance, it is going to be this distance of this generalized particle from this axis. If this is x, so this is going to be x cos theta, so this is going to be x sin theta. So moment of inertia of this particle about this axis is m by L dx, that is the mass of this, into m into r square, that is x sin theta its square. Integral, what is variable? X is variable, sin theta is not variable, theta is not variable, theta is a constant. For a constant theta we are finding the moment of inertia of this rod about this axis, of this thin uniformly massed rod about this axis. So x goes from 0 to L. So this comes out to be m by L. So obviously when sin square theta, this we can write it as x square sin square theta can come out because that is constant term. So m by L sin square theta, this is x square dx, so that comes out to be x cube by 3, 0 to L. So it comes out to be m by L sin square theta, that is L cube by 3. So this comes out to be ml square by 3 into sin square theta. This is the moment of inertia about y dash axis, So this way you can find the moment of inertia of, let's say, of this rod about this axis. We have taken so many cases. Now you can easily find the moment of inertia of this rod about any axis. And now you have also got a basic understanding of how we use integration in finding the moment of inertia of continuous mass distribution about an axis. Let's take some other examples.